is Matt Clay. We'll talk about L2-torsion of free-by-cyclic groups.
Okay, I'd like to start by thanking the organizers for inviting me to this conference. So I'm going to talk about L2-torsion of free-by-cyclic groups, which is related to what David spoke about on Tuesday. He talked about the universal L2-torsion of free-by-cyclic groups. So, I mean, there's some similarities here. There's going to be an L2 acyclic chain complex. I'm going to take the determinant of it. So that's what David did the other day. He took the determinant using algebra. He took the de Udane determinant, and then he took the polytope and started considering some norms. I'm going to take the determinant in a different way. I'm going to use analysis to take the determinant. Okay. But anyway, the motivation really comes from the same place. So it comes from considering mapping tori. So this is just a mapping torus of a surface homeomorphism where we take a surface cross an interval, glue the top to the bottom by the map, right? So F here is just homeomorphism. So as mentioned before, and also in Echo's talk, I mean, there's quite a history of studying the geometry and the topology of this manifold by looking at the dynamics of the homeomorphism. So there's been several results mentioned already. I'd like to mention another one that's going to be related to the work I want to tell you about today, and this is a result of Kojima and McShane. From 2014. It says the following. So suppose F is a pseudo-Anosov homeomorphism. Okay, so by work of Thurston, I mean, we know that the manifold, the mapping torus then is a hyperbolic manifold. So it has a volume, and you can ask how does the volume compare to the dynamics of the homeomorphism? And what they showed is the following. They show that the volume of the manifold is bounded by 3 pi times the absolute value of the Euler characteristic of the surface times the entropy. So log lambda f. So so this lambda f, this is the geometric growth rate that Echo spoke about the other day in her talk. So it's just how much the curve is getting stretched, sometimes called a dilatation. So you just take some hyperbolic metric on the surface, say, call it little sigma. Take the length of a curve, look at its iterates, and then take the kth power. Okay. Or if you also like, I mean, log of that is the entropy of the homeomorphism. And sometimes this quantity of the Euler characteristic times the entropy is sometimes called the normalized entropy. Okay. But they provide this bound here on the volume in terms of the normalized entropy. Okay. So I mean, one way to see a connection here between the left and the right-hand side of this inequality is using the geometry of Teichmuller space. So the right-hand side here, the log lambda f, that's the translation length of the pseudo-Anosov on Teichmuller space using the Teichmuller metric. And by work of Brock, the volume of the mapping torus is up to a multiplicative constant, the same as the translation length of the pseudo-Anosov using the Weil-Petersen metric. And the Weil-Petersen metric is bounded by a constant times the Teichmuller metric. And so that's one way to get some sort of, you can see a connection here, but I mean, they come up with a very explicit constant bound. Okay? But the main theorem I want to talk to you about today is a statement of this nature for free-by-cyclic groups. Okay. I don't think it's known to be sharp. I don't think anyone has. I think this sort of the slope is known to be sharp, or at least the right order. Okay, right. So free-by-cyclic groups. So let me just remind you what these are to set some notation. right, so these are groups that fit into a short exact sequence. Free group, the group G, and then Z. Okay, and of course, you can split this. So in fact, G is really a semi-direct product. Right, so I can write it as the free group with this extra generator T, and T conjugates X to some automorphism. Okay, and the the actual group then, so phi here, capital Phi is an automorphism. But really, this only depends on the outer automorphism. Changing phi within its outer automorphism class just really corresponds to taking T and replacing it by something times something in F. So really, this thing only depends on the outer automorphism, and that's how we'll denote it. So it only depends on phi, which is the outer automorphism class of capital Phi. And so we'll just denote it G sub little p. Okay? So that's the free-by-cyclic group. Okay. So for those of you that have studied outer automorphisms, I mean, you probably have a good guess as to what's going to go on the right-hand side of this equation. And based on the title of the talk, probably have a good idea of what's going to go on the left-hand side of this equation. So let me just say a few words about the L2-torsion now so that I can go ahead and state the main theorem, and then I'll explain what it is in a little more detail after that. So this was as defined by Luke. Okay, so so this is some Euler characteristic type invariant associated to an acyclic chain complex. What's the setup? So I mean, it'll work for a wider setup than what I'm going to care about here, sort of the types of groups that David mentioned the other day. It satisfied those properties he had listed over on the board. For today, I mean, let's just concern ourselves with free groups and surface groups. So setup here is just let G be a free group or a surface group. Okay, and then I'm going to take an automorphism of the group. All right, and then I can form the semi-direct product using this. And the L2-torsion is a number, okay? So different than the universal torsion that David talked about the other day, which was some element in this skew field. Well, this is also an element in a field, but right, so it's just a real number, okay? All right, and it's an Euler characteristic type invariant. So well, what I mean by that is, I mean, it's multiplicative under covers. So if I pass to the subgroup of finite index, it multiplies. And there are gluing formulas. So it really does kind of behave a lot like an Euler characteristic. So that's what it is. I'll say a little bit more about it in a little bit, but it's some number. And the motivation for saying that it replaces this left-hand side of the inequality is a theorem due to Luck-Schick. From 99 that says the following. So it's a more general theorem, but let me just state it in a way that works for what I care about today. So if I have a mapping torus, MF, so The mapping torus has a nice decomposition. So this is a JSJ decomposition. So I can break this thing up along tori. And I'll have two types of pieces. I'll have some pieces which are ciphered fibered. And then we'll have some hyperbolic pieces. OK? Yeah, I mean, if you have your homeomorphism, F, I mean, there's what people like to call the Thurston normal form. So I have some sort of canonical cut system of curves on my surface. And those curves, when I follow those through the mapping torus, they're going to provide these tori here that I have in this decomposition. And away from that, that canonical reduction system, the homeomorphism either is going to be pseudo-Anosov on some of the pieces, and those are the pieces that will kind of glue up and connect to give me the hyperbolic eyes, or it'll be finite order on the other pieces, and those are the ones that give me these. Okay? All right, and what Luck and Schick prove is that, right, so of course, the surface, the fundamental group of this guy is the semi-direct product of the surface group, and what they prove is that the volume of this manifold is proportional. Oh, sorry. Yeah. Sorry. Torsion of the manifold is proportional to the volume of the hyperbolic pieces. Yeah, so the torsion of the fundamental group is minus 1 over 6 pi times the sum of the volumes of the hyperbolic pieces. Okay. Yeah, so it really is a lot like Euler characteristic, right? Euler characteristic of a hyperbolic surface is proportional to the volume. And the same type of thing happens here, right? So for a hyperbolic manifold, the torsion is proportional to the volume. Okay? Yeah. So that's so my justification there for going to be replacing the volume over here with the torsion when I move to the free-by-cyclic groups. Yeah, and so the main theorem, I won't write it down exactly now, but it's an upper bound on minus the torsion of the free-by-cyclic group in terms of the dynamics of the outer automorphism. Okay? Right, so because of this theorem, right, you want to think of negative torsion as being the volume. So oftentimes just think about negative torsion. Yeah, and I should say, so it was proven by Luck that this quantity, negative torsion, is non-negative. Right. And if it could take negative values, maybe you wouldn't want to call it a volume. Okay? So it's at least bounded below by 0. So the main theorem I want to do is I want to provide an upper bound in terms of the dynamics, and like I said, it's going to look something like that. Okay? All right. So yeah, in order to talk about the dynamics, I need to say something about relative train tracks. So yeah, let me leave that one up there for now. So relative train tracks. So this is something like a Jordan normal form for your outer automorphism, how you should think about it. And this was developed by Vespina and Handel. All right, so what is a train track map for your outer automorphism? Well, so first off, it's just a homotopy equivalence. of a graph. So gamma here is a graph. This is the homotopy equivalence of a graph, which is inducing, the right outer automorphism, right, where I've already identified the fundamental group of the graph with my free group. Okay. So the homotopy equivalence inducing the right outer automorphism. There's a invariant filtration. So I can filter my graphs by subgraphs. Gamma 0 is the empty set contained in gamma 1, blah, 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 up to gamma sub capital S, which is the whole graph. And it's F invariant, right? So where F of gamma of little s is contained inside of gamma of little s. Okay? So for each one of these pieces here of the filtration, it's invariant under F. Plus 3 more properties that I'm not going to tell you about. But these properties do have a key dynamical implication, and I will tell you what that is. Okay? So there's 3 more properties here that I'm going to hide right now. Okay, but in order to sort of get to the interesting part there, I need to say what the transition matrix is. And this is exactly this F geo map that Echo defined the other day when she had a graph map. Well, it's the matrix representing that linear transformation. So we have this transition matrix. Denote it M of F. Okay, in the ijth entry of this matrix, it just counts the number of times you see the edge ej with either orientation in the image of ei. Yeah, so number of times ej with either orientation appears in F of ei. Okay? All right, so let's just look at a little example so I can highlight a feature of this matrix. Okay, so let's look at the map here in rank 4, which does the following. A goes to AB, B goes to BAB, C goes to CAD, and D goes to DCAD. Okay, so it turns out for this automorphism, just the obvious map on the rows in rank 4 is a relative train track map. And the filtration, so there's filtered here just 2 pieces. So gamma 1 is just the edges AB, right? A and B only map over themselves. And then the whole thing then is gamma 2. Okay? So this is the relative train track map for this automorphism, right? This bottom stratum is invariant. And what does the transition matrix here look like? Well, let's see. So let's just order things alphabetically, right? And so we can just read off what this matrix is. So A crosses AB, so I get 1, 1, 0, 0, and we just fill in the rest of it. Okay, right? You're just seeing what happens to B, C, and D. Okay? And the important feature here that I want to highlight about this matrix, that one of the things you get from the filtration, is that as long as you order the edges sort of in the obvious way, where edges in the lower elements in the filtration should be ordered first, this matrix has this block triangular format. Right? So there's these blocks here along the diagonal corresponding to what's going on the individual strata. Right? So if I look at one of the filtrations minus the lower one, right? this block here is just recording how many times C crosses C and D and how many times D crosses C and D. And of course, this one is just for the A and B. So yeah, and if you do this correctly, right, the infiltration property tells you that your matrix always has this form. So we're going to call this, that's MF sub 2 because it's on the second one, and that's MF sub 1. Right. So in general, right, we have these square matrices, MF sub S, which is just the submatrix corresponding to the S stratum. So that's what this is called if you take one of the filtrations minus the smaller guy. Okay. And the observation then is that this matrix, this is lower block diagonal with these submatrices on the diagonal. Oh, sorry, lower block triangular. With these submatrices on diagonal. Okay? Yeah, so that's sort of a important feature. Okay, and so yeah, what the those three properties that I didn't tell you about, what do they give us sort of dynamically? So the relative train track properties tell me that if I look at powers of the automorphism and do this construction, then the submatrix there exactly is just the corresponding power of the submatrix for the original guy. Okay? So if you, yeah, I mean, I should say a little bit by what I mean by f to the k. So I mean, apply f k times, but then tighten, right? So if you have some edge path that goes over something and comes back, you should tighten it. Because if you don't tighten, then in fact, this is essentially just the definition of matrix multiplication. It's not that interesting. So really what this statement is saying is that if you look at edges in the S stratum and you take their images, then the images that, or the edges that arise in the S stratum, they never go away, they never cancel. You never have to tighten those guys. Okay? All right. That's sort of the key dynamical feature here, these guys that we use. Okay. Okay, so you can always enlarge your filtration so that these submatrices are either irreducible or the zero matrix. And in the case that they're irreducible, they have a Perron-Frobenius eigenvalue. Which will denote lambda f sub s. Okay, so that's just a Perron-Frobenius eigenvalue for that matrix. And I want to just look at the ones that have greater than 1. So e.g. of f, this is just the indices where that eigenvalue is greater than 1. Okay, so these are the exponentially growing strata. All right, great. Now I can state the main theorem. Okay, so the theorem. So if f is a relative train track, then the L2-torsion of the free-by-cyclic group is bounded by the sum over the exponentially growing strata of ns times log lambda f sub s. And so I didn't tell you what this n sub s is yet. N sub s is just the number of edges in the strata, or it's just the size of the submatrix. Okay? All right, so that's the main theorem, is that we can bound the torsion in terms of the dynamics here of this relative train check. All right. So in the case that I'll put the so there's a corollary then in the case when it's irreducible, we get something that looks very similar to this. So if f is irreducible, then we get that the torsion is bounded by 3 times the Euler characteristic of the free group times log lambda f. And this log lambda f now, I mean, it's the prone frobenius. I mean, so in this case, when it's irreducible, I mean that there's only one stratum. So, the transition matrix itself is already irreducible. And in this case, I mean, this is just a prone frobenius eigenvalue for that matrix. And it's also, I mean, it's the growth rate, just like Echo mentioned the other day about, take a generic element in the free group, take some basis, and look at the cyclic length and see how that grows. Okay? Yeah, so I mean, where do you get this? I mean, well, this is just the most number of edges you can have in a trivalent graph. Okay, so yeah, a couple of comments. Let's see. So I mean, the Kojima-McShane result, I mean, is only stated for f pseudo-Anosov. Let's see. I guess I erased the Luck-Schick result. I mean, yeah. I mean, the point is that for a mapping class, it's really enough to sort of know what's going on the irreducible pieces, and then you can kind of put them back together. So if you wanted to get some statement bounding the torsion in terms of the dynamics for, say a mapping torus, I mean, it's enough to just know about what's going on the irreducible pieces, and then they all just sum back together. But for those of you that have worked on automorphisms of free groups, that's not the case. I mean, it's not the case that your typical automorphism of a free group is built out of, irreducible pieces that are stuck next to each other. I mean, this came up in Yael's talk when she was talking about the difference between, preserving a splitting and being irreducible. So it's normally not the case that you can just take a bunch of results for irreducible things and stick them together to get a general result. So it's kind of neat that in this case, I mean, it's essentially no more work to prove this one than that one. I mean, it's kind of nice that it works out this way, that you really don't care about I mean, what's going on here, right, is that C and D don't just play with each other, right? They also have A going on there. But you can essentially forget about that. I mean, essentially what I'm going to be doing is I'm going to be taking a determinant. And if you take a determinant of a triangular matrix, of a block triangular matrix like this, it's just the determinant of the things along the diagonal. And so that's really why it's kind of nice that you only really care about what's happening on the strata. You don't care about, how they mess up with the stuff underneath. So it's kind of a neat feature of this stuff, and I think it makes it kind of interesting. Okay? All right. Okay, so yeah, I guess I should tell you now what torsion is. No.
Examples?
Oh, well, examples. Yeah, that's something else to ask about. Yeah, I was asking if the Kojima-McShane result works for surfaces with punctures, then yes, that holds for that one as well too. And so I mean, in that case, right, in that case, the thing is a free-by-cyclic group. So if you go through, then using the, so then you'd want to put the, you could use the Luck-Schick result then to replace this with the volume. And I think my inequality, I think I could get like a 9 here instead of a 3. Yeah. Because their result, there's like a 6 pi, right? Yeah, so it's I don't know, it's 9 or it's something like this. I looked at it once and it wasn't any better, so then I forgot about what it was. But it's something like it's 9 pi. So. Okay. Yeah, so torsion. Yeah, so so the L2 torsion here, I mean, if you've seen Reidemeister torsion from the study of 3 manifolds, I mean, it's really the same thing, just with Hilbert spaces, infinite dimensional Hilbert spaces, as opposed to finite dimensional ones. But the idea is that it's a determinant of an acyclic chain complex call this C star of Hilbert spaces. Yeah, and just for now, go ahead and think these things are finite dimensional Hilbert spaces. Okay, this is fine. And then we'll switch to the infinite dimensional ones in a bit. Okay, so what does it mean to say you have an acyclic chain complex, right? So okay, so to say I have an acyclic chain complex really means that I can split these chain groups. Okay, so I can split these chain groups up, and I have that the chain map is going to map the A's onto the B's in dimension 1 lower isomorphically, and the B's go to 0. Okay, so really what it means to say I have an acyclic chain complex. Okay, right? Right, all of the cycles are boundaries. Right? Okay, and so yeah, so I have these isomorphisms from an plus 1 to bn and so forth. And what the torsion does is it just takes the determinant of these isomorphisms. Right, so the way that the torsion is defined of this chain complex. So yeah, so you could, so let me just write something down, I'll say something. Okay, so it's defined to be the alternating sum of log of the absolute value of the determinant of these isomorphisms, an to bn minus 1. Okay? So, I mean, some people will take the alternating product, right? Divide, multiply of the determinants. We're going to go ahead and take the log of that, so that the formulas really match the Euler characteristic type of, being multiplicative undercovers and getting the gluing, so you don't have the E floating around in all of those formulas. Yeah, so I mean, if you've seen the torsion before, I mean, I don't know, maybe log of the torsion, but I mean, I just want to think of this as being the torsion. Okay? So when I have the determinant, I mean, I have to tell you, some bases in order to compute the determinant. And well, just use any orthonormal bases to compute this determinant. Right, and so if I choose a different orthonormal basis, well, it's just going to differ by some unitary, and that has determinant absolute value 1, so this is going to be well defined. Okay? Okay, so yeah, exactly. So in the case when these things are finite dimensional Hilbert spaces, well, there you go. There's your definition. So in the context we're going to be working on our chain complex, here our L2-acyclic chain complex will have the chain groups there will, well, they'll be Hilbert spaces, but they won't just be, arbitrary Hilbert spaces. They'll be L2 of the group raised to some power. Okay, so it's tuples of L2 functions. And it's L2 over some group, so we have the group von Neumann algebra that's available there to help us. These operators here will be elements of the group von Neumann algebra. And so there's a tool from analysis that tells us how to take the determinants. So this is called the Fugletti-Cadison determinant. Right, so let me write down the definition here. So I have a operator, T, and I'll just think about this special case that we're going to have. So we have L2 of the group raised to some power, right? So just tuples of L2 functions, left invariant and bounded. All right, so the group acts on this thing on the left, and the operator should commute with the left action, okay? And bounded. All right, so yeah, really this will be like a matrix of elements from the von Neumann algebra. Okay, but so you're going to have these operators. These are going to turn out to be the boundary maps, and then you define the log determinant of this operator to be, so it's an integral of log lambda against the spectral density function. So this function nu sub t. So this function is just measuring the size of the subspace of things that are stretched at most lambda. So this thing nu t. So this is just a function from 0 to infinity, the spectral density function. And what it is yeah. So it's the von Neumann dimension of the subspace of things that are stretched by at most lambda. Okay. Okay, so why is this an appropriate thing to call a determinant? Well, let's just think for a second that we actually have just a matrix, okay? Just a matrix over R, and I want to compute its determinant. Well, so let's go ahead and suppose that it's a symmetric matrix, okay? So it's a symmetric matrix. So all of its eigenvalues are real, and it has an orthonormal eigenbasis. And so what is this function? Well, it's going to be constant unless you hit one of those eigenvalues, or the absolute value of an eigenvalue, right? And then it's just going to spike. And it's going to spike by exactly the size of that corresponding eigenspace, okay? And so this integral, really what it is it's just going to be a sum. And I just pick up at each of the eigenvalues exactly that multiplicity, okay? So I'm just going to get the sum of all of the eigenvalues with their appropriate multiplicity. So that's just log of the determinant. Okay, so that's essentially what's going on here as well too, right? So I'm integrating here, sort of, over the eigenvalues and picking up their multiplicities. Okay, more or less. All right. However, yeah, people who are a lot smarter than me can probably actually tell you more about this. The only bound that I need, which is going to look very similar to that, is a sort of obvious bound. This thing is always bounded by n times log of the operator norm. Okay? This function can only get to be n, and it hits that once you've hit the operator norm. So yeah, essentially how And you can prove this bound. But I mean, this is like the dumbest bound you could possibly have on the determinant of a matrix, right? Just take the largest eigenvalue and raise it to the size of the matrix, right? That's a bound on the determinant. Okay, that's what that is. Okay, great. All right, so let's go back now to the free-by-cyclic groups and say a little bit more what this torsion is. So apply this to the free-by-cyclic group. So yeah, so I need some complex. So we have the mapping torus, right? So now I'm just going to take the graph, same construction. Okay. And then what I want to do is I want to look at the universal cover. And I want to look at the chain complex for the universal cover. Okay, so what does the universal cover look like? Okay, well, so gamma, I'll see gamma, the universal cover of gamma will be a tree. And I'll see those trees sort of stacked horizontally. And they're connected vertically using the T action. So I'll see these universal covers of gamma. Say gamma 0, gamma 1, T acts by shifting everything up. And if I have some edge here, well, above each edge, one of these horizontal edges, there's a unique 2-cell. Right? And this 2-cell, well, the top part of it, what do I see? Well, I see, you know, I can take some lift of F to the universal cover as well, too, right? So this is some F tilde, which is supposed to agree with whatever automorphism you've chosen for T. And the edge path I see above this guy is just that edge path, and you know it's been shifted by T. Okay. Okay. So yeah, to make this a little bit easier to write, let me just think of L2 of the free-by-cyclic group. Let me just call that A. And so what does the chain complex look like? Well, the 2 cells, like I said, I mean, every 2 cell in the universal cover has a unique bottom cell. So I just need to think about these horizontal edges. And up to the action of the group, how many horizontal edges do I have? Well, it's just the number of edges in gamma. Okay? So my 2 cells, just going to be L2 of the group to the e power, right? So just an e tuple of functions here, right? So just L2 functions with the 2 cells. Then the 1 cells have 2 flavors. They're the horizontal guys. And then there's the vertical guys, right? And just like for the horizontal guys, every vertical edge has a unique bottom vertex, right? And those all come from gamma as well, too. And then the vertices, again, all just come from the vertex of gamma. Okay? So this is what the chain complex looks like. And so let me just denote this map here. So this is this boundary map. It gives you like a horizontal boundary, and it gives you a vertical boundary. And then over here, well, who cares? I don't know. This isn't going to matter, so let me not give those things some names. Okay. Yeah, so remember to define the torsion, right? I was supposed to split these things up so that I have isomorphisms. Well, this thing isn't quite split already, but it turns out it's really split enough so that I can really just think about forgetting about this second map here. And well, there's really 2 maps down here, and I can sort of forget about that first one. And really just take the determinant of this map here from the edges to the edges using a horizontal boundary, and this map from vertices to vertices using whatever map is there. Turns out that this guy here has determinant 0. And so what you get is that the torsion is just the determinant of this operator, just a single operator. Okay? But let me write down what this guy is, because it's really not that mysterious either. None of this stuff is mysterious once you think about it. Yeah, so this horizontal boundary operator, right? Right, so it just takes, in terms of the basis, right, it just takes an edge E and returns E minus TF tilde of E, right? You're just reading off the horizontal boundary of that 2 cell, right? So you disregard the vertical sides, and that's what the boundary of that 2 cell I have drawn there is, right? E, and then you have to go backwards along the top. Okay. And you can write this as a matrix multiplication. So this is right multiplication by this matrix. So it's the identity, right, that's coming from the first piece. There's this T, and then there's this matrix J, which is what's called the Jacobian. And it's essentially just the Fox calculus. So this is an E by E matrix over the group ring. Okay, so just over the group ring, no L2 anymore. But it's just right multiplication by this, where this matrix has the Jacobian. And how is it defined? Well, it's essentially just like the transition matrix. So you're going to count the number of times EJ appears in the image of EI, but you're not just going to count the number of occurrences. You're going to record where they are and what orientation you got. So this is the coefficient of EJ in F tilde of EI. And so this now is an element in the group ring over the free group. Okay. So yeah, you're thinking of, like you have your certain edges in the universal cover of gamma that you're identifying with the giving you the basis for your one chains. You just hit one of those with F tilde. Now you get a new one chain, which you can write as linear combination of these guys, and you just record the coefficient. Okay. So the observation here is that if I take this matrix and I just replace every element in it by its L1 norm, then I get exactly the transition matrix. Okay? So the transition matrix was just recording the number of occurrences, and this, like I said, has more information, right? So this one tells you where it occurs and what orientation you have. Okay? And so because this thing has that nice lower block diagonal form, so does this guy. Okay? Yeah, so let me just write down one more statement and then one more statement after that. Yeah, and so theorem. So this is really based on some work of Luke as well, too. Is that so the torsion then, right? So like we have written over there, it's log determinant, and let me just write now the actual matrix. Okay, but because this matrix has that form, this thing breaks up. Right, where JF sub S is the corresponding submatrix. Okay? Okay. Because anything that's worthy of being called a determinant, if you have a block triangular matrix, should just be the determinant of the blocks along the diagonal, right? Okay, and then from here you use a couple of more tricks and that bound, and you get the main theorem. Okay? Okay. But let me just say one more thing. So yeah, Luke showed that the minus the torsion, right, is greater than or equal to 0. I have an upper bound. You can ask, is it always 0? That would make my upper bound not that good. So when is this positive? So let's see. So the theorem shows that if there's no exponentially growing strata, it's 0. Okay. And if you go through using Luck-Schick's theorem and also the Kojima, if you go through using the Luck-Schick theorem, then you know that if this is, say a fully irreducible that's geometric represented as a pseudo-Anosov on the surface, then this is really just the volume. So it is non-zero. So there are things where it is non-zero, but you can ask when is it non-zero in general. I would conjecture that whenever you have an exponentially growing strata, it's non-zero. I don't have a proof of that, but I do have sort of a proposition that looks promising that tells you that the torsion is positive. So here's the proposition. So if there is an n such that for all chains, okay, so these are just one chains on the tree, okay, right? So just think one chain's on the tree, right? So E is just a set of edges. So these are just one chain, so finitely supported functions. So if there's some n such that for all chains, if you look at the L2 norm of that chain, 2 times it is bounded by the max of the L2 norm when you've applied f n times in the forward direction. Or let me just be a little sloppy and assume that it's invertible. Apply it in the opposite direction. So I should put a little star here or something. All right, so. All right, so the lift of f gives you an induced map on one chains, right? An edge just goes to a one chain. And so, if you know the Bessfina-Fein combination theorem, this is something like a flaring condition, right? Some sort of homological flaring condition. And if this is satisfied, then the torsion is positive. And moreover, even more interesting, you can write it as the integral of log lambda over complex numbers that are have norm greater than 1. So this kind of has some sort of similarity to you're looking at like the values of the spectra that are greater than 1. It's kind of related to one of the things that Mark had written on the board on Monday. Okay, great. I'll stop there. Thank you.
Any questions?
Yeah.
This last bit, I didn't digest it. Is this just being a toroidal? What is it?
Yeah, no. So a toroidal implies that if you have like a one chain that's an edge path, then this holds. Yeah. So.
Stronger or weaker?
Oh, this is definitely stronger than A. No. So yeah, this isn't going to hold for all F. But if you have something which is fully reducible atoroidal, I imagine this works. And then presumably you break things up along strata. And in the case when there are INPs, I have ideas. Just start easy.
If there are any other questions, let's thank the speaker again. So next talk at 11.